This one's going to be a bit more involved, so please do hang tight. Right, this is the Schrodinger equation. We'll start with the case of a particle in a box. The Schrodinger equation is IH bar and delta psi of xt over delta t equals h hat, and this here is the Hamiltonian operator, and this is basically the wave function psi of x of t, which is in the dimension x. The particle of mass m is in a 1D potential energy well, v of x. So the Schrodinger equation is given here as such. This is made up of time and a function of x, so we need a separation of variables as such. And this is the one in the box at the bottom here is the time independent Schrodinger equation, which we'll focus on. And the first one with the time element is very straightforward, solution of the differential equation, which is here. And now in the case of a 1D infinite square well, where v of x equals 0 inside the box, so minus h bar squared over 2m, and this is the Hamiltonian operating on the wave function, equals e of psi of x for x contained in 0 and L, while outside the box v of x is infinite, so v of x is equals 0 for x less than 0 and x greater than L. We now set the task of solving this part of the equation, the energy, eigenfunctions and values that emerge from discrete sets. So we talk about the nth eigenfunction psi of n of x, and energy, E of n, eigenenergy. The stationary state wave function is then this psi of n of x, e to the minus I e sub n t over h bar. Now apply some boundary conditions at 0 and L of 0, psi L equals 0, and returning to the general solution, which is psi equals a sine kx plus b cosine kx of the time independent Schrodinger equation inside the well, and applying boundary conditions. It is apparent, since sine of 0 equals 0 and cosine of 0 equals 1, that b equals 0. Then applying another boundary condition, psi of L equals 0, it follows that a sine k of L equals 0. A equals 0 is a trivial solution, which we discard because it's of no real use. So we take sine of k L equals 0, which gives k of L equals n pi, because we're always moving across in integer values of pi for n equals 1, 2, 3. So k sub n equals n pi over L. So the allowed energy values inside the well is psi of n of x, a n sine of n pi x over L for n equals 1, 2, 3, and so on and so on. And the energy values are given here of E of n, which is n squared pi squared over h bar squared over 2 ml, or this one here, and we recall that h bar equals h over 2 pi. Now the normalization condition. The normalization condition is integrating all over all the absolute values squared, which must equal 1 because the particle must be somewhere. For our case, x equals 0, x equals L. So we're integrating over this with our function that we've already determined here. And so with a little bit of algebra and substitution of values, we get this. A sub n equals square root of 2 over L. A sub n may be complex, so a sub n equals 2 over L e to the I sigma. No, delta, sorry. Where the delta is real and constant, but we set delta equals 0, so that e to the I delta equals 1 and a to the n equals 2 over L. So this is our equation here. And the stationary state wave function is here to combine with our first solution, encompassing time and the time-independent Schrodinger equation. When applied together, this becomes the full Schrodinger equation for this system. And now we can just, for a little bit of added information, we'll split this into a real and imaginary parts given here. And each case, the right hand side represents a sinusoidal or function of position, sine n pi x over L, scaled at each point by a time dependent factor. The time dependent factor is itself sinusoidal and oscillates with a period of Tn, 2 pi h bar over E sub n. Now, if we change from the zero potential energy and like shift it up up the axis to a v sub 0, now we will have these equations, and we're rearranging here. So this time our energy values are going to be here. So all the energy levels are raised by some constant v of 0, which makes no difference to the observed behavior. The stationary state wave function still vanishes outside the well, and our equation is now this for a non-zero potential energy. Now, choosing a symmetric well. Instead of placing walls at x equals 0 and x equals L, we will choose x equals minus L over 2 and x equals L over 2, giving v sub x equals 0 for x in negative L over 2 and L over 2, where v sub x equals infinity elsewhere. Now it's symmetric, where v sub x equals v sub negative x equals v sub x. So a symmetric well, we take our previous solution and adapt them by changing the variables again and extending this. We extend from x prime to 0 to xl of 0. It follows that the energy eigenfunctions of the symmetric square well are here after a little algebra, and so here where n is an integer, if n is even we get this, if n is odd we get this. The factor of cosine n pi over 2 and sine n pi over 2 are plus 1 and minus 1, so they are phase factors. We can just ignore those for these purposes. Right, the energy eigenfunctions inside a symmetric infinite well of length L, we have these, where the first is for even n and the second for odd n, which is sine and cosines respectively. The energy eigenvalues are same as before and given here, but for n and for odd. 2 and 3 dimensional square wells, these can be extended very easily from what we've already been through here. We first separate the time from the x and y. This will give us the dimensions x and y plus t, and we go through separation of variables again. These are the x's and y's, which we go on to separate as so, and we get this for e sub x, this for e sub y, and x of x equals a n sub x sine sorry, n sub x pi x over L, and y of y equals a ny sine ny pi y over L. And our energy values, this is for e sub x, e sub y, and x equals e plus y gives us our energy, which later on would be this, and this is the full stationary state wave function. And when we normalize, we go through the same process again. We get our constant normalization constant, which is 2 over L in this case, and then our full Schrodinger equation here given with the time component is what we get for these in these xy dimensions plus t. Now we can use the same process for 3D etc., which is just nx squared plus ny squared plus nz for energy, and the additional sine of x, and then this is going to be to the 3 halves, which is really straightforward to keep adding dimensions to these. We could go to higher dimensions if we want, but that would be a little bit silly. Now, note that we encounter degeneracy due to the symmetry of the 2D plus square wells. The state psi of 1, 2 is not the same as psi of 2, 1, yet some states have the same energy, so this is degeneracy. Now we'll move on to a finite square well now. We'll consider each part of the outside region separately, with the equations here 1 and equation 2 and alpha here, and these are the Schrodinger equations part for the time independent Schrodinger equation parts. And from equation 1 here, x is where x is negative, b sub x diverges, so we take b equals 0 and we get rid of that. Now in equation 2, where x is positive, the term FEAX diverges, so f equals 0, we get rid of that. Imposing these conditions then outside the well, we get this for x is less than minus L over 2, and this for x is greater than L over 2. This is a symmetric well, so for our normalization constants here, A equals G for even eigenfunctions and A equals minus G for odd functions. And this would be for the outside of the wells here. So one of the solutions could be a decay outside of the square well, and this isn't taking account of what's going on inside here. Could be something like this or whatever. That would be inside of the well equation, but these are for outside, these solutions, and they explain what's going on just here. And I think this is called in quantum mechanics, in physics, tunneling. But I have to stress here, I'm a mathematician, not a physicist, but I believe this is called tunneling, where there is a slight possibility that you could find a particle actually outside of the well, which is quite remarkable. And that's it for this talk. Please do subscribe, because there's plenty more coming. Thank you.